Hi, I'm Fernando Pereira from UFMG, and today we continue to talk about the usage of machine learning techniques in the analysis of programs. In the last class, we saw how to use a linear model to predict the impact of optimizations on programs. This time, we shall see how to use logistic regression to classify branches as taken or not taken. So the goal of this class is to classify branches. If we look into the control flow graph of programs, we see branches whenever we have blocks with two successors. For instance, in this CFG, we have two branches. Notice that we will be considering only blocks with two successors in this case. Blocks with multiple successors, like what you would get from a switch statement, for instance, are of no interest to us today. The classification problem that is related to branches consists in finding the direction of the branch that's the most likely to be taken. We shall mark this direction with the value 1. The other direction will be tagged as 0. 1 means that we think that the direction will be taken most of the time. So in this example, we believe that the first branch will divert the execution flow to the left side of the CFG most of the time. But mind it that the same branch can be taken sometimes and then not taken other times. We are classifying branches. However, there is a similar regression problem where the goal is to estimate the probability that a branch is taken. And there is even the problem of trying to guess how many times a branch would be taken. In this case, instead of finding probabilities, we want to compute frequencies. I mean, the frequency that some edge of the CFG would be traversed during any execution of the program. A stochastic solution to the regression problem was given recently by Murray et al. In that case, they were using a machine learning model to predict the number of times that each branch would be taken. That's what we usually call the problem of building a static profile of a program. The first problem, on the other hand, the classification problem, was studied by Brad Calder in the late 90s. In that case, he used a machine learning model to find the most likely direction taken when evaluating a branch. This is the problem that we will study in this class. But before that, let's find some motivation to this kind of work. In other words, what can you do if you have this information? The information that a branch is more likely to go some way or another. What could you do with it? Well, something that we can do is to find good layouts for the binary code. We can improve locality in the instruction cache if we leave instructions that are likely to execute together closer in memory. There are several ways to lay out the same program. Laying out the program means finding a place to every basic block once that program is converted into binary code. This is called linearization. We need to put the instructions that make up that program in memory. You can see possible linearization here, but this is not the only way to linearize this program. For instance, here's another way where we have swapped the two last basic blocks. The difference in performance between different linearizations can be pretty big. If you want to have an idea of how big, I recommend again the OOPSLA paper from 2021. Anyway, it's useful to find the most likely direction of a branch, as you can see, and that's what we shall do in this class. In this class, we will use logistic regression to classify branches. If we classify a branch as taken, then that means that we believe that the branch's non-conditional is more likely to evaluate to true. If we classify the branch as not taken, then it means that we believe that the conditional is most likely to evaluate to false. Logistic regression is a way to transform a linear model. Instead of using the linear model to do regression, we shall use it to do classification. Let's then go back to our original problem of branch classification. A branch is any bifurcation in our control flow graph, controlled by a conditional. So, given a branch, we want to tag a path out of it as the taken path and the other path as the not taken path. We will still use a linear model to this end. This linear model will be associating coefficients with some features. In this example, we shall use 6 features. Later on, I will explain what each feature is all about. But remember that our model will do classification, so we shall multiply the equation by the logistic function, which is usually called sigma. That's the formula of the logistic function. The logistic function is a type of sigmoid function. It has this name, sigmoid, due to the shape of the curve that produces. We shall take a look into that curve soon. Here's how we can write the function in R. That's a very peculiar function. Let's take a look into the form of the curve that the logistic function defines. We can do that using the plot function that's available in the R standard library. So here it is, the curve of the logistic function. Its domain is the entire set of real numbers. However, its range is the real interval between 0 and 1. We can use this curve to transform a continuous function into a categorical function. I mean, to transform the model that we use to do regression into a model that we use to do classification. Assume that we have two categories that are the target of our classification model. Every number n, whose sig of n is equal or greater than 0.5, belongs into category 1. That's just a convention that we agree on. We could use other thresholds. We are using 0.5 in this case, just for an example. And every number n, whose sig of n is less than 0.5, will be in category 2. For instance, let's consider the number 4. We get that sig of 4 is 0.98, more or less. If we agree that every number above 0.5 belongs into category 1, then we have that 4 belongs into that category. So going back to our classification model, what we are doing is using the logistic function to decide which category each feature vector will go. To compute PBR, we shall multiply the vector of coefficients, and in this case we have 6 coefficients. We will multiply it by the feature vector that we extract for each branch. I will show later how to get this feature vector. And in the end, we add the intercept to the equation. The final value, PBR, is a sigmoid of n. And we use this test to decide if the branch is taken or not taken. So we apply a conditional on the result that we get from the logistic function. Now let's take a look into these features. These are characteristics that we extract for different branches in the program. In this class, we shall use binary features. So each feature will be either 0 or 1. That does not have to be like this. We could use a wider domain for some of the features, but we shall be using binary features just for the sake of the example. Another characteristic of these features is that they depend only on the syntax of the program. They are absolutely static, so we can extract them by parsing the program. We shall be extract them from the program's control flow graph in this case, so each branch in the program's control flow graph will give you a vector with 6 dimensions. As a consequence of this static nature, the features are all deterministic. Given a branch, its feature vector is unique. And they are available, meaning that we can extract them in polynomial time. These 4 characteristics form what we call a static program feature, as defined in this paper about the classification of store instructions into silent or non-silent. Anyway, let's take a look into the binary static features that we chose for this class. Mind it that this is just an example. If you ever have to write a branch predictor, you can try other features. We have chosen 6 features that were used before in this paper that's about the static prediction of branches. The first feature is true if the taken part of the branch goes to a basic block that contains a break instruction. Well, in the case of a low-structured programming language, like the LLVM intermediate representation, it breaks basically any edge that leaves a loop. This kind of edges can be easily found using any structural analysis on the program's control flow graph. The second feature denotes if the taken branch is a back edge. This feature will be true if the taken branch goes to the header block of a loop that dominates the branch itself. It's a back edge. Then we have a third feature that will be true whenever the branch condition compares something against 0. Notice that in this case, all that matters is that the conditional uses the EQ operator and has 0 as one of the operands. It doesn't matter which operand. But notice that the condition must be the equal operation. We cannot do something with the outcome of this operation before testing it in the branch. So this last example would give us 0 for this feature because it's negating the equality operation. This feature would be false for this last example. The fourth feature will be true if the branch uses at least one non-constant operand that could be 0. I'm calling this feature is 0, but perhaps the best name would be non-constant operand could be 0, but that name would be rather long. For instance, in this example, we have two branches. Can you see these branches? The first branch contains a non-constant operand that could be 0. That's because we assigned 0 to variable I, the first operand of the branch. The other branch contains an operand 0 of I, which does not contain a dependency to the constant 0, so the feature is false for this branch. We can compute this property with static analysis. But can you think about the static analysis that computes this feature? That's not difficult, just compute the backward slice of each operand of the branch and see if this backward slice might contain the constant 0. Our fifth feature is true whenever the taken side of the branch goes to a block that does not post-dominate the branch. So here's an example where the feature would be true. That's because the taken basic block is not the post-dominator of the branch. And here we have an example where the feature is false. The taken block is the post-dominator of the branch. Finally, our sixth feature is true if the taken block contains a function call. For instance, here we have a call to function foo within the block that's the destination of the taken path. But again, this is just an example. In that paper from where we took the 6 features, there are some 30-something more features that we can use to describe branches. Let's now make this presentation more concrete with an actual example of a model implemented in R. I left some data that we shall use in this class in the CSV file. This file contains 9 columns. 6 of these columns are the binary values of the features. 0 means that the feature is not present, it's absent. 1 means that the feature is present. And the last column is the outcome of the branch. Whenever we have a 1, that means that the branch was taken. Mind it that this CSV is artificial. I invented the data. Well, I do have an actual CSV with an actual data, but it's just that I wished to simplify this presentation and then I, came up with some data. That's just a disclaimer, but it bears no consequence to the class. So here's the entire program that we use to carry out logistic classification in R. Don't worry, I will go over each line. We start by reading the file with the branch features. Then I'm shuffling the data just to make our results more interesting. I do not know if you've noticed, but the features appear in the order of the binary numbers that they form in the CSV. First we have the vector with 6 zeros, then we have the vector with 5 zeros and a 1. After that, the vector that denotes the number 2 in binary format, and so forth. The CSV has 64 vectors. So shuffling is good. In these 4 lines that come next, I'm simply separating the data into a training set and a test set. we will use the training set to calibrate the model, and we will test the accuracy of the model in the test set, of course. Here's where I'm training the model. Well, there's a lot of stuff going on in this line, and we shall take it slowly. First thing to know is that I'm using R's generalized linear model. It supports the logistic function as a wrapper on the vector multiplication, just like we saw in the beginning of this class. The taken column gives us our dependent variable. That's the scalar response of the linear model. We are working under the supposition that this variable depends on the independent variables, which are the 6 binary features that we are considering in this example. Once we've trained the model, we can use it to carry out predictions. Notice that we are performing predictions on the test set. Here, we will consider a branch as taken, as A1, if the result that we obtain after applying the sigmoid on the features of the branch is greater than 0.5. Once we have predictions, we can count misses. And then our accuracy is 1 minus the number of misses. If we use 80% of the data as our training set, we get a pretty high accuracy. This time I got 0.91. But mind it that this result depends on how you've shuffled the data, so you can get something else next time you run the same lines. The accuracy drops a bit if we use less data to calibrate our model. I'm now using only 60% of the data in the training set. If you want to see the values that we found for our coefficients, you can invoke the summary function on the model. These are the values that we got. The coefficients are here. For instance, the coefficient of the break feature is minus 88.19. Can you in any way interpret the meaning of this negative coefficient? Well, in a way, it means that we are unlikely to take a branch that leaves a loop. In other words, branches usually don't terminate loops. That's more or less intuitive. If we expect a loop to run for, say 10 iterations, the chance that a branch terminates the loop is only 1 over 10. Another thing that's interesting, our model consists in the application of the logistic function onto a linear combination of features, in the sense that we do not, for instance, multiply one feature for another. The consequence is that all the features are treated as independent of each other. But sometimes it makes sense to consider interdependencies between features. For instance, let's consider these two features, 0 and EQ0. Let's imagine that we know that x in this example does not depend on the constant 0. That means that the E0 feature is false for this branch. Then this branch is a bit less likely to be taken. But our model cannot account for this kind of interdependencies. We can mitigate this problem by adding this nonlinear factor to the model. In R, we can write the model exactly like in our equation, simply multiplying one variable by the other. And with this last observation, I close this class on logistic regression in compilers. The list of features that we have used in this class have been taken from the work of Moreira et al. In that case, she was computing the probability that a branch is taken, so it was a regression problem, not a classification problem. She would use these probabilities to build a static profiler, and with it to improve the performance of BOAT, a binary optimizer that's integrated with LLVM. The original formulation of the branch classification problem comes from a paper by Brad Calder and others. That paper is from 1997. Notice that they use a slightly different set of features. In particular, they were working directly on the C or on the Fortran programming languages, not in a low-level language like we did in this class. And there is a very nice example of how to use logistic regression to determine the best optimizations for Java methods in this paper by John Cavazos and Michael O'Boyle. Anyways, that concludes our overview of classification problems in compilers. If you have questions, feel free to write to me later on.